Hi, my name is Ellie Hecker, and this is my Lab 3 on magnetic fields of bar magnets. The purpose of this experiment was to investigate the magnetic field of permanent dipole magnets and gain a better understanding of distance dependence in magnetic fields. Using the Biot-Savart law, I calculated the magnetic field of the bar magnet at different observation locations and found that the distance dependence n was negative 2.8723. The magnetic moment mu was 5.223 am squared, and the magnetic field at 45 degrees experimentally was 2.533 e to the negative 0.5, 3.5 e to the negative 5, 0 teslas, and computationally it was 1.1448 e to the negative 5, 3.43439 e to the negative 5, and 0 teslas. Some of the main physics principles used in this experiment were the magnetic field produced by the Earth, the distance effect on magnetic field, which tells us that the further away from a source we will have a smaller magnetic field, while closer to the source we will have a larger magnetic field, the Biot-Savart law for a point charge, and the magnetic dipole equation, and the bar magnitude equation, which I have attached screenshots of here. I began the process to complete this experiment by compensating for magnetic north. The magnetic field of the bar magnet needed to be orthogonal due to the Earth's magnetic field. I aligned my phone with north using the Teslameter app, showing that the x component needed to be equal to 0. I lined a ruler along the bottom of my phone to measure east and west. Using GeoMag in this location, I found that the B net was 49 teslas. Next, in order to find my magnetometer chip, I aligned the bar magnet with the ruler and then slid my phone along the perpendicular line until the x component was at a max and the y component was at a min. After marking this position, I rotated my phone 90 degrees and repeated the procedure until the x component was at a min and the y component was at a max. I marked the positions as shown in the figure and then used this location to measure my values. This shows my measurements and observations for on-axis. I recorded distances where the x component of the magnetic field of the bar magnet were equal to 20, 70, 120, 170, and 220 microtau. I noticed that the x component of the magnetic field increased as the magnetometer moved closer to the magnet, and it approached 0 when the magnetometer was far from the magnet. The following data shows my off-axis measurements at different distances of dperp. I used these measurements along with the magnetic field of the Earth at these distances to calculate the experimental magnetic field. A logarithmic graph was used to show this data, which followed an equation of y equals negative 2.8166x minus 13.7758, and you can see that the magnetic field decreases as the distance decreases. The slope of this line was n, which represents the distance dependence, negative 2.8166. I used the negative 13.77 to solve for k by taking the natural log and came up with a value of 1.0466 e to the negative 6, and then plug this value into the equation shown here to solve for the magnetic moment, which resulted in a value of 5.233, as you can see these calculations in the bottom right. So in writing my code to create computational model to represent these magnetic fields, I first defined constants and then the magnet and magnetic field functions using my previous calculations in the Biot-Savart law, which is shown here. Next, I wrote code to calculate the magnetic field and entered different observation locations, both on axis and perpendicular to the axis, and created arrows to represent these fields. Last, I did the same thing to calculate and represent the magnetic field 45 degrees off axis using the dperp that I calculated earlier. My computational model is shown here. The orange field represents the magnetic field on axis, the blue arrows represent the perpendicular magnetic field, and then the purple arrow shows the magnetic field at 45 degrees. To summarize my results, I observed that the magnetic field differs depending on the observation location that is used. I found the distance dependence to be negative 2.8723, and using the percent difference equation, I used this value and our theoretical value for n to calculate a percent error of 4.257%. The magnetic moment was calculated to be 5.233, and the magnetic field at 45 degrees was experimentally found to be 2.533 e to the negative 0.5, 3.5 e to the negative 5, 0 teslas, and computationally it was 1.14 e to the negative 5, 3.43 e to the negative 5, and 0 teslas. The percent error for the magnetic field was calculated to be 19.67%. In conclusion, if the magnetic north had not been compensated for at the beginning of the experiment, then our magnetic field would not be on axis, which would result in inaccurate Teslameter readings and calculations for k, mu, and n, and we would have a greater percent error. If we were to stick two identical magnets together end to end and redo the experiment, then the magnetic field would increase significantly because the two bar magnets would be oriented in very similar ways, therefore increasing the field. Thank you so much. If you have any questions, please let me know.